on this computer. All right, if someone would like to play with the chat there, see if I can't see what you're saying there. Cable, share. Let's see. Nobody at home is chatting with me? Okay, participants do, okay. There we go, hello, thank you. All right, so where we ended last time, we were talking about intramolecular interactions, okay? What makes a molecule want to get near another molecule at the outside? Yes.
So since the homework due on Wednesday is over chapter 2, is the homework still going to be due on Wednesday? That's over chapter 3.
No, I'm going to push that.
Okay.
I'm going to push that. Thank you. Send me an email.
Okay.
And tell me to push that chapter. I want to. We're going to only have it over 1 and 2, and then chapter 3 will be in the next quiz.
Okay, thank you.
We will be caught up pretty soon here, before the first exam, for sure. Okay. The question was the homework still going to be due on Wednesday? And the answer is no. Just our quiz through IR is going to be on Wednesday, and then that will be pushed back slightly. And we should be back on track fairly soon. Okay, so we were talking about these intramolecular reactions, how to squeeze these molecules together. And we saw that there were different ways to do this. And the last thing that I didn't get to really describe was the molecule itself can have both hydrophilic and hydrophobic properties. There's nothing that says the whole molecule has to dissolve in water, or the whole molecule has to hydrogen bond, or the whole has to induce dipole. When you have different parts of the molecule that are interfacing with different types of interactions, you have these things that we sometimes call amphoteric, or something that has a hydrophilic side or can hydrogen bond, or has a dipole that it can bond to. And then it'll have a non-hydrophilic side or a hydrophobic side, scared of water. Basically, it only has those induced dipole. And those exist in many, many molecules as well. But the idea here is that general trend of if you have a strong group, like a hydrogen bond or a dipole, you can get up to 5 carbons per type of functional group, per type of interaction. So you can get some really complex things in the solution because of different interactions. Okay, any questions on intermolecular forces? Intermolecular, not intramolecular. Okay, because our summary of this is our strongest is, of course, the ion, cation, anion. Sodium chloride, it melts at like 3,000 degrees. Then we have our covalent bonds, which are next. That's the ones we're going to deal with most. So instead of giving away electrons, we are now sharing electrons. Okay, so that's next. Then we have ion dipole, because your ion is still a permanent ion, but it's being shared amongst the partially positive or negative portion of the dipole in a huge shell of a whole bunch of different molecules, and they're sharing that charge. Next, we come with our strongest bond we're going to see in our solutions and stuff we have here, which is hydrogen bonding. Comparatively, it's weak, but it is one of the strongest ones we have besides the covalent bonds. And then the dipole, remember, there has to be a permanent polar bond. Permanent polar bond, right? And then, of course, it helps if all of the polar bonds don't cancel out to give us not just a polar bond, but a polar molecule. And then our last one are the dispersion forces, induced dipole, which are very, very weak. Okay, so when we looked at our different functional groups, right, we talked about different bond types, and we talked about carbon, oxygen, hydrogen, and the different bond types. Now I want to use infrared spectroscopy to show you that these bonds do exist, and these types of bonds are found in different types of functional groups. So the whole point about IR spectroscopy or infrared spectroscopy is that we can actually see which bonds are of the right energy to absorb light that is below red. Okay, below red. So it's lower energy than red, and that means there's an energy associated with the bond, and we can tell the difference because it'll absorb or not. So the way we have this is we just have a light source, and then we put our sample through and we shoot light through it. And some bonds are going to absorb certain energies and some bonds aren't. And so we're looking for what gets absorbed, and that tells us we have that type of bond. Okay, so the electromagnetic spectrum is actually pretty, pretty big. The little piece we see with our eyes is really tiny. Okay, and it has a certain energy associated with it, and it works for us for the most part. But then we go a little bit higher in energy, and we have the ultraviolet range, and we can even use that within chemistry to tell us something. So visible range will tell us whether the compound is blue or red. The infrared, the ultraviolet will actually tell us how many double bonds we have nearby each other. But IR, which is just below that, just below visible, is going to tell us what kinds of bonds we have. Then we're actually going to end up way over here in microwaves eventually when we start talking about our nuclear magnetic spectroscopy. So we're going to use microwaves and radio waves in there. So in chemistry, we actually use visible light, UV light, infrared light, microwaves, radio waves, and guess what? We can also use X-rays, gamma rays, and contact rays to do different things as well. So we can use different parts of the different energy spectrum to tell us different things. But I want to talk about just this one just below visible right now, because that's the one that's going to tell us some cool things about our bonds. Before we get there, I'm not going to do any math, but I want to show you where the equations come from. The three things we got to figure out is, number one is frequency. The number of waves per second. So this is per second. So it's hertz per second. So that means if light is traveling through space or whatever and has 5,000 cycles per second, it has a frequency of 5,000. Okay, that is different than wavelength. Wavelength is what is the peak to peak distance of those waves, okay? And they are proportional. So in our equation here, we see that our frequency is proportional to the speed of light time divided by the wavelength, okay? So in a case where you have the speed of light is faster or slower than what you've learned because it's going through a different medium, you can actually say, okay, well, frequency is proportional to wavelength, okay? Now, the other thing we can find out is if we play a little with our numbers is that our frequency times a constant is equal to energy. So frequency is equal to energy, okay? So that means if something absorbs at a certain frequency, it's interacting with a certain amount of energy. So frequency equals energy. Now the equation here is Planck's constant times the frequency here, but we can also do it where we have Planck's constant times the speed of light divided by wavelength. And all of this gives us an idea that we have so many waves per meter, inch, centimeter. Turns out in IR spectroscopy, we use the phrase per centimeter as our unit here. So we're going to actually see where we're going to have a thing that's going to be our wave number. The little frequency with a little tilde over it is going to be designated as our per centimeters. Centimeters to the -1. Okay. So whenever we look at an IR spectrum, you'll know it's an IR spectrum because it's going to be from 4,000 to 400 reciprocal centimeters or wave numbers. Centimeters to the -1. So you can also think of it as 1/centimeters. That's an M. Okay, so those are the units we're looking for. Okay, so that's not very big, but if we look at the energy associated, that means that we have bonds equal frequency. So different energy should show up in different areas of our spectrum. Okay, so when we're thinking about that, we have to think about, okay, why is it absorbing an energy? Well, if you look at your covalent bond, you have an atom and an atom, and they're sharing electrons between them, okay? So that means the electrons between them have found this nice, convenient little space, or this average place for them to be in between those two nuclei. So our bond lengths are our average bond length, okay? But there's a little bit of flexibility in this. It kind of moves back and forth like a spring. So if you think about two carbon atoms, they're sharing their electrons. Their average distance is like 1.5 angstroms, okay? But they're oscillating a little bit. Now, if you have the energy to make it oscillate more, or you hit the right energy, it's going to absorb that energy and oscillate more. And if you're absorbing that energy, you can see what kind of bond it is. So that's what we're looking for when we're talking about this. Most of the bonds, most of the things we're going to be talking about are what we call stretching modes. So imagine there's going to be a spring between two atoms. And in some cases, it's going to be a heavy atom and a light atom. Imagine the little antenna things where it's wiggling around really fast. Then some of them are going to be heavy atom next to heavy atom. And imagine it just being kind of like this. And then sometimes you're going to have more than one bond. You'll have two bonds or three bonds, and they're going to be going like this because they're held together so tightly. So we want to look at those, think of those springs as different amounts of energy and the wavelengths as different amounts of energy. So we should be able to see a trend in our system. Yes?
So does it work with double bonds?
Does it work with double bonds and triple bonds? Yes, it does.
Oh.
Yeah, we'll get to that. But that is a great observation. We'll see how that changes. Now, let's go ahead and take our scan. Again, at home, you don't have to, but please do if you can. It shows up on my Google Sheets. So. If it doesn't work, just email me your seat number. That's fine too. 3, 2, 1. Okay, so while we're going to talk about those spring motions most, there are other things that happen, and there's different things where they stretch in the same direction, they stretch in opposite directions, they wag in one direction, they wiggle this way, they waggle, they do all these other things, and those tend to be lower energy and absorption, and so we tend to see them in a certain area of the spectrum. But the ones I want to talk to you most think about as those springy, those spring constant between the two different atoms. So if you learn nothing else about IR, know this chart. Okay, if you know nothing else about this chart, about IR spectroscopy, know this chart. Now, I want to explain to you why these different regions equate to different energies. Okay, so the first region I want to talk about is, well, the idea that, number one, we have wave numbers here at the top. So notice we have this little per centimeters thing here. So we have between 4,000 wave numbers and between 400 wave numbers. So the 4,000 wave numbers is higher per frequency, so it's higher energy. And then the 4,000 is lower energy. So this is the higher energy side because of the higher wave number. Okay, so that's the first thing I want to say. Second thing I want to say is there's going to be 3 types of bonds between 2,500 and 4,000 wave numbers. And they are all what I call heavy atom, light atom bonds. So it's stuff bonded to hydrogen. Carbon hydrogen, oxygen hydrogen, nitrogen hydrogen. They're all bonded to hydrogen. And the way I want to think about those is that you have a big atom and you have a small atom. And if we think about it springing around, the big atom's not going to move very much, but the small atom's going to be springing around like this. Okay? So it's going to be moving fast and have this energy associated. It can absorb energy and move around quite a bit. Okay? So all of the big atoms, small atoms are above 2,500 wave numbers. Okay, now we can shift them around based on energy, and we'll talk about that next. But like we were alluded to earlier, how does that work with double and triple bonds? Well, okay, if we had this heavy atom and this light atom, and it's going to have the highest frequency because it's going, What's the next thing that's going to have the next highest frequency? The one that's bound tightest. So it's going to be triple bonds. Ooh, they're bound tight. They're bound by sigma bond and 2 pi bonds. And so we have our acetylene, carbon-carbon triple bond, and our carbon-nitrogen triple bond, our nitrile. Okay, so light atom, heavy atom, 2,500 to 4,000. Then we have our triple bonds, 2,000 to 2,500. Only thing in that range. Not true. Actually, sulfur hydrogen's in that range, but we're not going to use that now. The next thing we have, if triple bonds were the next highest energy, we're going to go down to double bonds now. So in the double bond range, which is 1,500 to 2,000, we're going to see carbon-carbon double bonds, carbon-oxygen double bonds, and carbon-nitrogen double bonds. Okay, and then below that are going to be the single bonds, the sigma bonds, 1,500 and below. Okay, in that 1,500 and below region, though, we call that the fingerprint region because that's where some of that wagging and wiggling and stuff comes out. And it's not always as well defined as the other 3 zones. So the first 3 zones are most important. And then that fourth zone gives you that reliability that says, ah, yes, I do have a carbon-carbon bond because I have something here. Okay, so that's the zones. Do we understand why they're in different energy places? These all have hydrogens, the highest energy. Triple bonds next, double bond, single bond. Yes.
When I was on the homework and I was looking at the IRF problems, then each locale should have a different energy, right? Because they would ask you about specific ones, but like if you have like a complex compound, then there would be like multiple regions with higher level. It's just like the one
Yes.
bond that's doing
Yeah, so that's a great question. The question was on the homework, if you had like a functional group that had a carbon-oxygen double bond and a carbon-carbon double bond and an oxygen-hydrogen bond, are you only going to have one absorption? No. Each of those types of bonds is going to absorb in their correct region.
Yeah.
So you have to, if you have a thing with multiple types of bonds in it, you want to make sure it's your compound. You want to make sure it checks all of the types of bonds that you think you have. Yes.
Isn't hydrogen like a strong bonding? Like strongest bond.
Hydrogen bonding. I'm going to talk about that. That does play a role.
Okay.
Hydrogen bonding does play a role. It changes the shape of the peak. But right now, I want to talk about these are the lighter atoms, and they have that. Now, the next most important thing besides having the right energy in the right zone is how intense the signal is going to be. The intensity of the signal increases with the polarity of the bond. The more polar the bond, the difference between oxygen and hydrogen is greater than nitrogen and hydrogen, which is greater than carbon and hydrogen. Therefore, the OH bond is more polar and is more intense than the NH bond, which is more polar and more intense than the CH bond. So polarity leads to the intensity. Yes.
I just wanted to say that the 400 weight number is that the higher energy?
No, 4,000 is higher in energy. See, the increasing energy goes this direction. Increasing wave number goes that direction.
Okay, that's what I thought. I just thought you said 400. So
No, 400 is our lowest energy, and 4,000 wave numbers is our highest energy.
thank you.
Okay, so now that we have polarity gives us intensity, and the different bond types give us region, we should be able to identify all the different kinds of bonds we have in a compound. And by knowing all the kinds of bonds, you should know the functional group, because your functional groups aren't just one kind of bond most of the time. So let's put that into play. And in this chart, what I want to show you is polarity changes intensity. So let's look at our triple bonds here between carbon-nitrogen triple bond and carbon-carbon double bond. Carbon-carbon triple bond is weak to medium. It's weaker than the carbon to nitrogen because there's a bigger electronegativity difference between carbon and nitrogen than carbon and carbon. So it can be weak in the carbon-carbon bond because it can be a non-polar bond, less polar, less intense. Okay, so let's look at our double bonds too. In our double carbon-carbon double bonds and carbon-nitrogen double bonds, they're both medium, but one of those, question, sorry.
So that's because wavelength, increased wavelength it's all based on energy. That's why that makes sense. Because
Wave number equals energy.
it's all in energy, like describing varieties of energy.
Right. Well, what you're saying is that this kind of group will absorb this kind of energy, and that kind of energy is associated with that wavelength of light.
Okay.
Okay, that amount of energy is associated with that wavelength of light. Okay, so now let's go to look at here. We have CO, CN, and CC double bonds. Okay, the C carbon double bond and the carbon nitrogen double bond are not very polar. They're right next to each other, so they have medium to weak intensity. But the carbon oxygen, which is one more over, is always strong. It is a stronger, it's a more polar bond, it's a more intense signal. Well, that gets us to this weird one right here, benzene. It can be strong or weak because, you know, that, remember, this is not even the real structure. This is only one of the many resonance structures it could be. So that can change from strong to weak. So we'll see some weird things happen here, including some splitting and some weird things. So we're going to see that happen. But now if we go to these right here, these carbon oxygen, carbon nitrogen, they're going to be strong because of the polarity for this one, medium for the polarity in this one, but they're both going to be below 1500 because they're both single bonds. Okay, so intensity follows polarity. Okay, now let's look at our last three here. All three of these have pretty, this one's less polar than that, and this one's up. If we look at all of these, they're all above the 2500 wave numbers, but this OH is stronger than this NH, which is stronger than our CH, because those are decreasing in bond polarity. So now we can see different types of bonds: single bonds, double bonds, polar bonds, non-polar bonds. Ooh, we can start building a molecule. So let's put this to practice, okay? The first thing I always do when I look at my spectrum is, number one, does it have wave numbers on it? Because that means this is going to be my high energy side. And the first thing I always do is I draw a line at 3000 right here, and I'll show you why. Okay. Now, the reason I draw the line at 3000 is that's going to tell us something about carbon hydrogen bonds. I've said that carbon hydrogen, oxygen hydrogen, and nitrogen hydrogen are all 2500 and above to 4000. Okay, so that means that's where those are going to show up. But carbon changes on how the hydrogen bonded to carbon changes position based on the carbon's hybridization. So if it's below 3000, we're looking at an sp3 hybridized carbon with a hydrogen on it. And then if it's above 3000, it's going to be an sp2. Just take that right now. I'm going to show you another spectrum. Okay, so what we're saying here is that because of this, we have an sp3 hybridized carbon, which means we have no double bonds and no triple bonds. Let's make sure that's true. So let's go to our triple bond region, which is 2500 to 2000. Oops, sorry. That's 2500, it's down here. Let me erase that. $2,500 to 2000 is our first zone. Our second zone is 2,500 to 2000. Sorry, our first zone is 4,000 to 2,500. Our second zone is 2,500 to 2,000. Okay, in this zone here, this is only C triple bond, C and C triple bond N. And notice we don't have a peak here. That means our compound that we just took this spectrum of does not have a carbon-carbon double bond. It does not have a carbon-carbon. Now, I alluded to the fact that we have to have that if it had an sp2 hybridized carbon with a hydrogen on it, it would be above 3000. So let's look to see if there's a double bond. Well, the double bond would show up between 2000 and 1500. So there's nothing in that zone either. And so what we're seeing in this next zone down here, these are the double bonds. And we don't see a bond there either. We don't see a peak there either. So that means our compound doesn't have that. But it does have stuff below 1500. And so that's going to be our carbon-carbon peak, or our other WAGs, our carbon-carbon single peak. So from just what we see here, you have sp3 hybridized carbon with hydrogen on it. We have no double bonds, no triple bonds. We only have carbon-carbon bonds. Okay. So that's what we can tell from the spectrum. Now, what if we change things? What if we added a double bond? Is it going to change? And yes, it will change. So the first thing we want to do is say, okay, is there a double bond? Again, starting way up here, start at 3000. You have a peak above 3000 and you have a peak below 3000. That means you have a carbon that has a hydrogen on it that is sp2 hybridized. So, and then these are sp3 hybridized carbons with hydrogen. Why? When you hybridized your orbital, you had one s spread out over 4 equal orbitals. It's 25% s. S is the small round one, right? So when you take it and spread that s out over 3 equal orbitals in sp2, that makes it higher in energy. It goes up in wave number. And now when you go to sp, you spread one s orbital out over 2 hybrid orbitals. And if there's a hydrogen bonded to it, that is now half s orbital, and it's going to go up even higher in energy. So you can tell the difference between an sp3 hybridized carbon hydrogen, an sp2 hybridized carbon hydrogen, and an sp hybridized carbon. So that means you can tell the difference between an alkane, an alkene, and an alkyne just by looking at 3000. Cool, eh? So let's double check, make sure everything else is there. We have nothing in our 2500 to 2000 range. So we don't have any triple bonds, but we do have 2 peaks above 1500. So what do we talk about intensity? The more polarizable, the more polar the bond is, the more intense it'll be. So we actually have a small, weaker peak here from a stretch, but then we also have this stronger peak here. And if we look at the part here, that carbon-carbon bond is not perfectly symmetrical. It has one carbon on one side and no carbons on the other, leading to a medium intensity peak. Okay, so we have a medium intensity peak. Then everything else is below 1500, and those are those carbon-carbon single bonds and WAGs and wiggles, etc. Okay, so how we prove to ourselves we only have double bonds and single bonds, and we only have carbon and hydrogen, just by where our zones are. Cool, right? So let's see what happens when we throw a benzene ring in there. Remember, benzene ring, this is not its exact structure. This is one of the many structures we can draw. So what we're going to see probably is maybe some double bond stuff. We're going to see some carbon, some hydrogens bonded to sp3s. So let's draw our line at 3000 again. If we draw our line at 3000, it actually comes right to here. And we'll see that the sp3 is just below 3000. But guess what? This is an sp2 carbon that has that hydrogen on it. It's just above 3000. So we have sp2 and sp3 in our system. But we should also have some double bonds, right? We shouldn't have any triple bonds, we should have double bonds. So if we go to 2000 to 1500, that's blank. Good, that we were expecting it to be blank. But now we have these weird things here. When we have, if we draw our 1500 line, it just barely, this includes it barely. Okay, so we have, again, not one structure, not one resonance structure. We just have one representation of the many. So we have these combination of bands that have different energies because they're different, more or less double bond character at any one time. And then we have a nice peak here and a nice peak here. But then we also have all of our other peaks down below 1500. Okay, so what do we know? sp2, sp3, hybridization, we can tell the difference. We know where to look for our double bonds. What happens if we have a triple bond? Well, that's going to move it to that zone that we haven't played with yet. So we do what we did the last time. We draw our line at 3000. And our first band is 2500, which is right here to 4000. And we see that we have sp3 hybridized carbons, and we have an sp hybridized carbon with a hydrogen on the end of it. What if that alkyne was in the middle of a chain and not at the end? We will not have that hydrogen. You have to have a carbon, specifically an sp hybridized carbon bonded to a hydrogen to get that peak above 3000. And notice it's right around 3300. 3300, be right here. So we've gone from below 3000 to 3000 to 3100 for the sp2. And now with the sp3, we've gone to 3300. We've walked it down, more S character, higher energy. Okay, but what if we didn't have a hydrogen there and we still thought we had an alkyne? Well, we look at our next zone, the 2500 to 2000 range, and we see a stretch in that range. There's only two things there, so it's got to be an acetylene or a nitrile, and we think it's an acetylene. And then we look here and we have a little teeny peak here, but I think it's just a impurity until we get down to 1500, and then our carbon-carbon bonds down here. So just starting up at our 3000, we see we have sp3 hybridized carbons with hydrogens on them. We have an sp hybridized carbon with hydrogens on them. Looking at zone number 2, we have a triple bond. Looking at zone 3, we have no double bonds. Looking at our last zone, we have carbon-carbon single bonds. Does that make sense? We're following the energy. Start from 4000 and follow the energy down. Okay, so those are kind of cool, and you know, those are some neat bonds. What about the carbon-oxygen? Carbon-oxygen hydrogen bond. So I said before that we had an oxygen-hydrogen bond is going to be in our first zone, our 2500 to our 4000 wave numbers, okay, because it's a heavy atom light. And then somebody said, wait a minute, doesn't the oxygen and the hydrogen there hydrogen bond? Well, yes, it does. And that's what makes the shape of the OH bond so big and wide. There's so many different ways for it to hydrogen bond, it spreads out the different kinds of energy it can absorb. So you always got that big wide peak. But that big wide peak is always above 3000 and usually centered around 3200. So 3200, 3300. That's important because that changes when we go to a carboxylic acid. So 32 to 3300, always about 3000, big and broad. Okay. Now, in this case here, we're looking at a compound that doesn't have any double bonds. It only has carbon-carbon single bonds. So we have our 3000 line. So we have sp2 hybridized, I'm sorry, sp3 hybridized carbons with hydrogens on them. No double bonds. We have no triple bonds, no double bonds. And then right here at 1500, we have our carbon-carbon single bonds, our carbon-oxygen single bonds. In fact, we notice we have more peaks here than we used to. It's probably going to be that carbon-oxygen bond that's going to show up there, and it's going to be more intense than the carbon-carbon bond because polarity of the bond influences intensity. Okay, so does that make sense? What happens when we change out that oxygen and it's no longer has a hydrogen on it? If the oxygen doesn't have a hydrogen, it's not going to absorb in that high energy band. So if we draw our line at 3000, we switch that carbon oxygen hydrogen bond to a carbon oxygen carbon bond. We got rid of the hydrogen, we get rid of that high energy peak. But we have a really good peak down here below 1500, probably the carbon-oxygen-carbon bond. And we only have hydrocarbons. We have nothing in the rest of the zones. Here's 1500. So we've switched our carbon-oxygen-hydrogen Brid-Brogg peak, completely went away. And now we only have our carbon-hydrogen peak and our carbon-carbon peak and our carbon-oxygen. Does that make sense? So we can actually watch the functional group change just by looking at this spectrum. Okay. So then I said you have to be careful about the OH peak and where it shows up. And the reason you have to be careful about that is because of the carboxylic acids, okay, which we'll get to. Okay, so let's see. We've covered carbon-hydrogen peaks. We've covered carbon-oxygen peaks. We've covered oxygen-hydrogen peaks. Nitrogen-hydrogen peaks. Okay, so nitrogen, hydrogen are going to be up in that high range above 3000, right? But nitrogen's really cool because if you have 2 hydrogens on your nitrogen, it'll have 2 peaks. And they'll be slightly broad because of hydrogen bonding. If you have 1 hydrogen on that nitrogen, you'll have 1 peak and it'll be slightly broad. If you have no hydrogens on that nitrogen, you have nothing in that range. So we can actually see how many peaks we have above 3000 and see what we have. So these 2 peaks right here are associated with the nitrogen with 2 hydrogens on it. There's 3 peaks there, man. What's that other peak? The benzene peak here has the sp2 hybridized carbon hydrogen. So that's what that other peak is. And then these are the CH3s there. And then we have our carbon-carbon double bonds that are associated with our benzene ring. And then 1500, and then we have our CN stretches and our carbon. So the key to remember here in your nitrogen is if you have 2 peaks, you have 2 hydrogens, 1 peak, 1 hydrogen, 0 peaks, 0 hydrogens. But see how every kind of bond in that entire structure is represented. Every bond is absorbing in its correct range. That's what you need to really focus on when you're looking at IR. Focus on it absorbing in the correct range. Okay, so not that I wanted to do that. I wanted to say on that one. There we go. All right, so let's go for that last thing that's in that second range. We had a carbon-carbon triple bond, and that's the first one we did. Now we have the carbon-nitrogen triple bond, and it shows up in that 2000 to 2500 range. And if we look at the structure, it's a long chain right here, and then just this carbon triple bond. So if we draw our line at 3000, we see nothing above there. 2500 to 2000. Wow, there's a nice sharp peak there. Our carbon nitrogen triple bond. And then nothing until after 2500. So we have sp3 hybridized carbon with a hydrogen on it. We have a C double bond, triple bond N. We have no double bonds. And then we have single bonds below. Make sense? Okay. So that covers all of our range. No, that only covers our high range and our mid range. Now we have to do our double bonds. Okay, so in the double bonds, we also have, besides our carbon-carbon double bond, which we've talked about, we have our carbon-oxygen double bond, our carbonyl compound. And we saw that when we did the functional groups, we had a whole class of functional groups that were based on that carbonyl compound. And remember that the carbonyl right here is permanently has a nice polar bond with that oxygen there. So carbonyl groups always absorb between 1500 and 2000, and they are always strong in intensity. Okay, but they shift around depending on what's attached to them. So if we have a carbon and then a hydrogen, at least one hydrogen on there, it's an aldehyde. And if we look at the electronegativity of hydrogen and carbon, they're about the same. Okay, which means that our aldehyde carbonyl and our ketone carbonyl are going to be about the same place. And it's going to be right in the middle of the road. And so if you look at this, it's focused right around 1700 for both the aldehyde and the ketone. little high, little bit above 1700, 1715, but they're centered right there in the middle because they're about the same electronegativity as hydrogen and carbon are. So they're both about the same. But if we were to go there and add an electronegative element that had lone pairs on it, it's going to shift it above 17,000. They're all above 17,000, almost 1750. So you're never going to, your aldehydes and ketones can be right there at 17,000. Sorry, 1700. Delete, delete, delete. 1700 wave numbers. And your esters are always going to be a little above that because of that electron donating group here. So if that does it, what about a carboxylic acid? Well, a carboxylic acid, because it also has a polar bond here, it can actually help pull it up even higher. Notice the carboxylic acid is even higher than the ester because of that weak, or that hydrogen-oxygen bond, where the oxygen is more polar than, more electronegative than hydrogen. It's pulling the electron density in, and then the carbonyl is pulling electron density as well. And then we go backwards and go to the amide. Again, it has a lone pair, but it goes below 17. Why does it go below? It's, oh, wait, hold it. It's not as electronegative as oxygen. It's closer to the same electronegativity as carbon, and it's got a lone pair. So it's going to be below that of a ketone, which would be with just a carbon bonded to it or just a hydrogen bonded to it. Okay, so we can walk through all these different carbonyl compounds and say, okay, aldehydes and ketones are right in the middle. Esters and carboxylic acids are higher in energy. Amides are below that energy. All right, does that make sense? So again, this is all where they are in that range between 1500 and 2000 wave numbers. So let's use some examples here. So in the case of just the carboxylic, just the ketone, the ketones and aldehydes would be about the same. We see, again, draw our line at 3000. We only have aliphatics. We have a strong peak above 1500. See how strong that peak is? Intensity, carbonyl, C double bond O. Okay, and then we see nothing else. The other thing that is not in your book that I think you should know is that there is a hydrogen on aldehydes. Okay, that hydrogen on aldehyde is actually shifted in a very weird place. It's right here at 2750. So if you have a peak here at 2750 and a carbonyl peak here, you actually have an aldehyde. It's that carbon, that hydrogen on that carbon. Okay, it's shifted below where you'd think it would be, but you know, that's why I wanted to draw attention to it. But the carbonyl is right here in the middle, right here at, look at that, 1700 almost. Okay, so yes.
So is that how you would tell the difference between an aldehyde and a ketone?
Yes, that is the only way to tell the difference between an aldehyde and a ketone on an IR. Okay, so that clock's wrong. All right, yeah, all right. So now I said watch out for that hydrogen bonding peak in the OH. If it's an alcohol, that OH peak is brought in always above 3000. The OH peak in a carboxylic acid is centered on 3000 and covers that entire range. See how if this was just an alcohol, this big peak would be over here. But because it's the carboxylic acid, it actually overlaps 3000. That's the big difference between the alcohol and the carboxylic acid. What's the other big difference between an alcohol and a carboxylic acid? The alcohol doesn't have a carbonyl peak, but the carboxylic acid should. In fact, it should be what, above 17,000 or below above 1700 or below 1700? Slight, yeah, above, like up to almost up to 1800. So 1750 to 1800. So let's look at that. Ooh, right here. Right above the 1700s, about right here in the middle. So it's above 1700. So we have a CO peak that's above 1700, and we have that big wide thing that covers 3000. Carboxylic acid right away. Questions? And let's see, there's no double bonds on this, so That's all we can see on this one. Then everything else is below 1500. All right, so now let's talk about amides. Okay, I said amines are kind of funny because what you'll see is if it has one hydrogen on it, it'll have one peak. If it has two hydrogens, it'll have two peaks. The amides are exactly the same way. The difference between an amine and an amide is the amide will have a carbonyl peak. The amine will not. So we're going to see our spectrum and say, oh, look, two peaks above 3000, and they're kind of broad. So we have two hydrogens on a nitrogen. Do I have an amine or an amide? Well, let's see, 2000 to 1500. Ooh, big, huge peak. Here's 1700. Ooh, it's just below 1700. Carbonyl peak below 1700. Two hydrogens in the nitrogen range. It can't be an amine. It must be an amide. And it has two hydrogens. Questions? Okay, so that is my last slide on IR. So what is the takeaway here? Know the zones, know where the different types of bonds are in the zones. Make sure whatever compound you think it is has all those types of bonds absorbing in the IR. Intensity is directly correlated to polarity. Energy is directly relatable to wave number. Okay. So again, when you think about it, you can discover many, many different functional groups by saying one of these, two of those, one of those, one of these. Every single functional group should be represented here by where it does or does not. All right, any questions on that?
So the math that we were looking at, that wouldn't be like something we would be tested on. It would just be like, it's just for like us to understand.
No, this is organic. If you can't draw it in sticks, I don't think it's a good idea. So, I can do the math, I just choose not to. So let's go to chapter 3. Okay, I have 15 minutes. And so I want to get through the first 3 things in this. The first thing I want to say here is that this is actually not on my slides, but I want you to go to Canvas. In Canvas under resources, the first document you see is the 5 things that can happen in a reaction mechanism. The first thing you'll see is 5 things that can happen in a reaction mechanism. And I'm going to go through all of them today, okay? But they are add a proton. Ooh, if you have acid in something, it might add a proton. Take away a proton. If you have base in something, it might take away a proton. Rearrangement. It might find a more stable configuration. Break up a bond to form a stable molecule or ion. We're going to see that today. And the last thing is a partially positive or positive thing attacking a partially negative or negative thing. We call that the reaction between a nucleophile and an electrophile. Just write that one down and we'll talk about that more later. So there's only 5 things that can happen in a mechanism. But let me tell you about how we write mechanisms so you can understand what we're going through here, okay? So the first thing we want to talk about when we're talking about organic mechanisms is what the hell is a mechanism, okay? It's a thought process of how you make and break bonds in a chemical reaction in a logical way, okay? So we have to start with, okay, what's a chemical reaction? Well, a chemical reaction is just when we have a reagent, like let's say compound A is reacting to form compound B, and then it's reacting with something here. So our compound A is what we typically call the substrate. Okay, substrate. Okay, the substrate is the thing that's reacted on by the reactant. R here, let me change that to, let's see, not R, but Y. Let me change it to Y here. Y here is our reagent. It's the chemical compound that's changing the substrate. B is the product. Okay, So the important thing here is there's a line here. That line goes in one direction and goes with an arrow. That's telling you that reagent Y is making compound A into compound B. Okay, so usually this reaction goes from left to right. And usually the substrate and the product are written out and the reagent is occasionally put over that arrow. Okay. Now, is that the only thing we're going to see on these? Well, no, not really. We're also going to see some additional information sometimes. Like sometimes they'll tell us the solvent or the temperature or maybe something else right here. They're going to tell us more information. And so you want to look for that arrow and look for that additional information because that additional information might change your mechanism. Okay, so let's figure out how we're going to do that. So the first thing we got to play with is the idea that we're going to have something that's going to react right here, something that it's going to, some reagent it's going to react with, and then some product. Okay. So that's the way we typically see. So this is the thing that's reacting, this is the reagent, this is the product. But what if instead of doing that, we had this and this? Notice we don't have a double bond anymore. And we do H nu. That H nu is telling us we have something else going on. That's telling us we have light. We don't have a double bond. We took bromine and got rid of the double bond. Here, we're not doing that. We have different information, and as a result, it gives us different products. So paying attention to what's reacting and what the product is, and what the reagents are, and all the information given is very important. Okay, so you can also have things like CH3, CH3, and we're going to say a 1 here, Me, MgBr, and a 2, H2O. When you see this, what it's telling you is this compound is going to react with this reagent first. When it's done reacting, it's going to react with this reagent second. So they're going to give you this reagent, and then they're going to hold off, not add any water, wait until the reaction's done, and then add water, and then finish the reaction. So those numbers tell you the order in which the reagents were used. Okay. So let's see. All right. Questions on that? Okay. So we're still trying to figure out, how to write these things. So in a reaction mechanism, we're trying to figure out how the bonds broke and formed to make our new thing, right? And we can do it in a couple different ways. We can have A going directly to B, happens all in one step. And we call that a concerted reaction. In concert, it happens all at once. We're making and breaking bonds all at the same time. Okay. The other way to do it, though, is to go from A to some reactive intermediate. It's not our final product, but it's going to react a little bit more to give us our final material. So A is still our substrate, B is still our product, but we had to go through some reactive intermediate to make our mechanism make sense. Okay, so think breaking a bond to make a reactive species or something like that. So when we're talking about that, we want to make sure that we're consistently writing things such that we know where the bonds are being made and bonds are being broken. So what are bonds? Bonds are pairs of electrons. So we have lone pairs, right? We moved those around when we did resonance structures. So when we're talking about mechanisms, we want to see where the electrons are flowing. The electrons from a bond to make an electrons for a new bond. We want to look at the flow of electrons. So to look at the flow of electrons, we're going to do a new arrow. We're going to call it the curved arrow. Okay, in the case of the curved arrow, we're gonna have a curved arrow with 2 points on it, okay? Curved arrow with 2 points on it. The reason we have 2 points on there is we wanna show you that we're moving 2 electrons. 2 electrons. So 2 points, 2 electrons. Because we do have one with only 1 point on it. I'll show you that later. But we also have something where we can have the reaction that's gonna go in one direction. It might be a little different and go in the opposite direction. 2 minutes left, okay. All right, if we have the reaction going in one direction, but it could have, so we made some product B, but then product B reaction goes back to A, we can have what we call an equilibrium reaction. Think acid-base reactions in Gen Chem. We can have that equilibrium happen. So when we have that happen, we have a different kind of arrow. So that brings us to my last slide for today, the different arrows we have for our reaction mechanism. The first one is the reaction arrow. It's a single arrow going in one direction, going from reactants to products. Okay. The next one is a double arrow, one on top of the other, saying there's an equilibrium between A and B. Not equal, it's just somewhere in between. Okay. But that's very different than our resonance arrow. Remember, our resonance arrow is double-ended on both. Those are our resonance structures. And somewhere in between is our resonance hybrid. And then we have our full curved arrow with 2 barbs on it, moving 2 electrons. 2 electrons. And if we're only going to move 1 electron, we put 1 on there, 1 electron. Okay, so now we have some tools to help us understand how mechanisms work, where the electrons are flowing, and how we're going to make them flow from one place to the next. All right, questions on that? All right, quiz on IR on Wednesday. All right, any questions in the online group here? All right, I'm going to go ahead and stop sharing and stop recording.